Hey guys, welcome back. We're starting a brand new chapter. It's chapter 9, and today we're looking at 9.1 multiple representations of functions. You will not be caught off guard with some brand new math. You will be eliciting prior knowledge. So what that means is you've got the tools to approach these problems. They're just contextual. They got stories. You kind of gotta organize your thoughts. Okay, so let's go and look at 3 examples here. Right, really, I can't provide one example and have you assume they're all going to be solved the same way. So it's more about looking at what's given and how we can start and proceed from there. Okay, but again, you should be able to handle the math very easily. All right, let's see what's going on here. A manager at an amusement park monitors the ticket sales at the park over a 4-day weekend. Match each situation to one of the following graphs. Sketch a possible graph of the situation if the situation does not match any of the given graphs. Okay, so situation A, the park closes on Friday for repairs. Okay, if we're looking at sales on the y-axis and the days of the week, or during this 4-day weekend, excuse me, as the on the x-axis, I would think that if the park was closed on Fridays in terms of sales, there'd be none. I should be looking for a Friday of 0 sales. So I'm thinking this graph. Okay, let's take a look. And graph 2, the graph shows the ticket sales on Friday. Good. Situation B, the park hosted a big concert on Saturday and a parade on Monday. A big concert on Saturday. What are we thinking the sales were like? Some of us might assume high. And a parade on Monday, we would also think they're pretty high. So in terms of answer, what would be the correct choice? All right, here we have graph 3. The graph shows increased ticket sales on Saturday and Monday. Okay, so compared to the other days, you would expect peaks, and graph 3 indeed provides that. All right, so by default, you might know what situation C's graph is, but this one says the park was very busy during the holiday weekend. So because the entire weekend would be busy, sales presumably would be high. Graph 1, the graph shows high ticket sales every day. Okay. All right. So you'll have something similar like that to work on. Again, trust your... Okay, the second example says, Kurt is rappelling down a 500-foot cliff at a rate of 6 feet per second. Create a table equation and graph to represent Kurt's height from the ground with relation to time. When will Kurt reach the ground? So a lot is happening here. Let's go ahead and I've listed it here as steps. So let's go down that list. Okay? They want us to create a table first, right? So let's go and let T be time, which happens all the time, in seconds, and H be Kurt's height in feet from the ground. Kurt begins at a height of 500 feet, we're told, and the height decreased by 6 feet each second. Now, to produce a table like this, okay, we'd list a couple of seconds. Okay, we're going to go from 0 to 5. We're going to start off with the initial height of 500 and minus 6 from there for each successive feet. Right? The next thing they want us to do is to write an equation. So let's kind of refresh your memory how to process this. We know that the height is equal to 500, right, at the initial time, minus the 6 feet per second. Okay, we've got the language down from the story. To turn that into algebra, we'd let h equal height, okay, equal to 500 minus 6 feet per second. We can simply multiply 6 times t for representing seconds. Okay, and next, what they want us to do is graph to represent Kurt's height from the ground with relation to time. So for us to graph it, always a good idea is, if possible, have an idea what your intercepts are. So let's go ahead and kind of review how you operate that. Right? Now we do know that we're calling it the h-intercept here, okay, or the y-intercept is 500, okay, because that is the initial height. Now what we're going to do is try and find this other intercept here. So basically, when the height is 0, when he's officially on the ground, what is that time t? Okay, so because we do have our equation h equals 500 minus 6t, and we do want as an intercept h to be 0, right, when he's on the ground, We'll plug in 0 for age and basically let the math speak for itself. We'll subtract 500. We'll divide both sides by -6, and we get 83 1/3, and that is our t value. Okay, so officially 83 1/3 would be our x-intercept. Therefore, to answer this last question, when will Kurt reach the ground? Kurt will reach the ground after 83 1/3 seconds. All right. Let's move on to a final example here. This one says, Stacy runs 3 days a week at a track. Stacy starts keeping time when she starts warming up and notes after 2 laps how long she has been at the track. The table shows the time for several laps. Use a graph and an equation to find the time it will take Stacy to run 20 laps. Alright, so apparently Stacy starts keeping track at 2 lap intervals. And at 2 laps, she's been there 30 minutes. At 4, 16. At 6 laps, 19, 8, 22. And at 10 laps, 25 minutes. Visually, we can see that there's an increase of 3. So chances are that this has a linear relationship. So anyways, as far as what we've been requested to do, use a graph. If we were to plot that data, we'd have something that looks similar to this, right? Laps as the x-axis, time as the y-axis, and indeed it is very linear. So that's good to observe. The data does appear to be linear. Okay? Therefore, in terms of our next request, writing an equation, we go ahead and produce a linear equation for step 2. Okay? We're going to let x be the number of laps with which we've discussed and y the time in minutes. So for us to produce a linear equation, right, we definitely need slope. So as a refresher, you've got m equals y2 minus y1, x2 minus x1, and really you can take any 2 points, okay, from the graph. We'll start off with the first 2. For example, this would be y2. We can use this as y2, and this is x2. This is y1, x1. Okay. So that would produce 16 minus 13, and 4 minus 2 is 2/3 for the slope. And again, you can use any 2 points. We plug it in essentially into this point slope form. Okay. Now this is equivalent to the slope-intercept formula, which most of us are accustomed to, y equals mx plus b, but this one is just as adequate. Okay. So in this case, we're going to have y minus y1 equals the slope times x minus x1. And in this case, we had already declared that this is y1, this is x1. So we plug it in here with the slope. And after some very basic math, we go ahead and get y equals 3/2 x plus 10. Okay. Now, if you're tied up with the math, kind of work it out there on the side there at home. If for some reason you're struggling, we can look at it at home, in class. But again, this is very Algebra 1 like. Okay. All right. So there's the equation, and they want us to find the time it will take Stacy to run 20 laps. So to what we're going to need to do is evaluate the function for those 20 laps, and it will look something like this. We've got our linear equation, y equals 3/2 x plus 10, and since we're going to evaluate for 20 laps, we'll plug it in for x. Okay, we do the basic math, and we get 40 for y. Therefore, it will take Stacy 40 minutes to complete 20 laps. Guys, we hit the 9-minute mark. I can't wait for you guys to bring questions and comments and concerns to class, and I'll see you guys tomorrow.